Hi everyone. In the last few classes we have discussed about compact operators and their properties. Today we will discuss about a representation of compact self-adjoint operators. So let us look at some important properties of these operators. So let us start with the lemma. Let T be a compact self-adjoint operator. Then we can say that either norm T or minus norm T is an eigenvalue. We know that when T is self-adjoint, either norm T or minus norm T is a spectral value, but when T is also compact, we are claiming that norm T or minus norm T is an eigenvalue. Let us look at the proof. So we have that numerical radius of T is exactly norm T, or we can say that norm T, if you write in the numerical radius form, it is supremum mod inner product Tx with x, where x is coming from the unit sphere of H. Choose a sequence xn in the unit sphere such that modulus of inner product T xn with xn converges to norm T. Now we can choose a appropriate subsequence. So choose a subsequence if needed. xn k of xn we should write, but we are denoting the subsequence in this with the same sequence xn of xn, so denoting with xn itself. For notational convenience, because we have to deal with another subsequence again, such that inner product T xn with xn converges to lambda, where mod lambda is norm T. This we have seen earlier also. We can use the polar decomposition and get a subsequence. Okay, now we want to get a subsequence of xn such that this and a vector x such that Tx equal to lambda x. Okay, now let's consider, so as xn is bounded and T is compact, so there exists xnk, a subsequence of xn such that so T xnk converges to y. Let us say the limit to be y. Now consider norm of T xnk minus lambda xnk square. This is nothing but express this in terms of inner product. This is T xnk minus lambda xnk with itself xnk minus lambda xnk. This is nothing but norm T xnk square plus mod lambda square, because xnk is a bounded sequence, so mod lambda square inner product, and we know that xn's are coming from the unit sphere. So again this is minus 2 real part of lambda inner product T xnk with xnk. We know that inner product T xnk with xnk is a real number because T is self-adjoint, and lambda is also a real number because spectrum of T is subset of R. Okay. Now norm T xnk less than or equal to norm T square, so that is mod lambda square plus mod lambda square minus 2 real part of lambda inner product T xnk with xn. Now we know lambda is real and the inner product is real, so you can, this is 2 lambda inner product T xnk with xnk. Now this goes to 0 as k going to infinity, because inner product T xnk with xnk converges to lambda, so we can conclude that, so T xnk minus lambda xnk converges to 0 as n tends to infinity. Now we know that T xnk is also converges to y, so from this we can conclude that lambda xnk, we can write this as let us say minus lambda xnk. We can write T xnk minus lambda xnk minus T xnk. Now the first term goes to 0 and T xnk converges to y, so on the whole this goes to minus y as k going to infinity. That means we can say that xnk converges to y by lambda as k going to infinity. Now we also know that T xnk converges to y and T is bounded, so also T xnk converges to Ty by lambda, but this has to be equal to y because T xnk converges to y, so therefore we can say that Ty is lambda y. So we can ask the question whether y is 0 or not. If y is 0, what will happen is that T xnk converges to 0, and we know that xnk also converges to 0, so that means inner product T xnk with xnk converges to 0, but we know that that is lambda, where lambda mod lambda is norm T. In that case T becomes 0 operator. So but we are looking at a non-zero operator, so let us take T to be non-zero, so we can conclude that y is non-zero. So that means we got lambda to be eigenvalue and y the corresponding eigenvector. And here we use the fact that compactness of T to show that there exists a subsequence xnk such that xnk of xn such that T xnk converges to y. For that argument we have used that compactness of T. Okay, so the conclusion is that when we have a compact self-adjoint operator, then we can conclude that either norm T or minus norm T is an eigenvalue, because lambda is a real number such that mod lambda equal to norm T, so either lambda is norm T or lambda equal to minus norm T. So the point spectrum of T is non-empty, so corollary, if T is compact and self-adjoint, then point spectrum of T is non-empty. But this is not the case all the time. We have seen if you drop the self-adjointness, we can get a compact operator such that point spectrum is empty. So let us look at one example. So earlier we have discussed this example. Define k from L to 0 1 into L to 0 1 by kf at s is integral 0 to s ft dt for every L to 0 1. So we have seen earlier that spectrum of k is singleton 0. We have shown that spectral radius of k is 0, and in fact we can show that 0 is not in the point spectrum by looking at the definition. Okay, so that means when you drop the self-adjoint, this operator is not self-adjoint, because k star f at s is nothing but integral s to infinity s to 1 ft dt, so it's not self-adjoint. So that means we cannot drop the condition that k is self-adjoint. Now what will happen if you drop the condition that t is compact? So one more example. So let us look at define, let us take for all t01, define the multiplication operator induced by f from L201 into L201 by mf at g is f into g for every g in L201. Okay, so that means mf g at t is nothing but t times g of t for every g is. So this is a multiplication operator induced by f of t equal to t, and we know that spectrum of mf is exactly range of f. This is closed interval 0 1, and we also know that the point spectrum of mf is an empty set. Note that this operator is not compact. mf is not compact, so it's a self-adjoint because this is mf bar and mf bar equal to mf, because f is a real valued function. So this operator is self-adjoint but not compact. So if you drop any of these two conditions, we cannot get eigenvalue. So if you assume that the operator to be compact and self-adjoint, you can get an eigenvalue. Now we can ask the question that what will happen if you repeat this procedure, because once we get an eigenvalue, look at the corresponding eigenspace and restrict the operator to the corresponding eigenspace, and then also it is compact and self-adjoint, and you continue this process. So if you do that, we can get the spectral theorem. Actually we can get a spectral representation for a compact self-adjoint operator. So to prove the spectral representation theorem, we need few more results. So let us quickly recall. So T restricted to any closed subspace is compact for every closed subspace M of H whenever T is compact. This we already have observed. For a self-adjoint operator, every eigenspace is reducing. If T equal to T star, every eigenspace reduces, because every eigenspace is invariant, and if you have an invariant subspace for an operator T, its orthogonal complement is invariant under T star. But when T equal to T star, we can say that an eigenspace is always reducing. And the other result that we need is the lemma that we proved, that it has an eigenvalue, either norm T or minus norm T is an eigenvalue. Now using these three results, we can actually prove the spectral representation theorem. Okay. Now using these three results, we can prove the spectral representation theorem. Next we prove the spectral theorem for compact self-adjoint operators. Theorem. Let T be a self-adjoint compact operator defined on Hilbert space H. Then there exists an orthonormal system phi 1, phi 2, phi 3 of eigenvectors of T with corresponding eigenvalues lambda 1, lambda 2, lambda 3, so on. In fact, we can arrange them in the decreasing order, mod lambda 1 bigger than mod lambda 2 bigger than so on, such that Tx can be represented as summation n equal to 1 to infinity lambda n inner product x with phi n multiplied by phi n for every x in H. So let us call this equation as 1. If lambda n is infinite, then we can say that lambda n converges to 0 as n tends to infinity. The series on the right hand side of the equation 1, actually the series represent series of operators, and we can say that converges to T in the operator norm. So the series of operators on the right hand side, RHS of 1 converges to T in the operator norm. Of B of H. So this is a statement of the spectral theorem. So we will give more consequences about the spectral theorem after giving the proof. So let us look at the proof. So to understand this proof, we divide the proof into 3 different steps. The first one is step 1, constructing eigenvalues and eigenvectors. So the construction of eigenvectors. To get eigenvalues and eigenvectors, we use the earlier results again and again. For example, we proved a lemma which says that there exists an eigenvalue for a compact self-adjoint operator, that is nothing but either norm T or minus norm T. So we use this result to get eigenvalues and corresponding eigenvectors repeatedly. So let us take T1 as T and H1 as H. Then by lemma 1, there exists lambda 1 in R and a unit vector phi 1 such that T phi 1 is lambda 1 phi 1 and mod lambda 1 is exactly norm T1 or norm T. That means lambda 1 is either plus norm T or minus norm T. Now by the projection theorem, H can be written as span of phi 1 with orthogonal complement with span of phi 1 perp. So let us write H2 as span phi 1 perp. then T can be written as, with respect to these two spaces, span phi 1 and h2. So let us say this is span phi 1, this is h2, span phi 1. We have seen this earlier. This is lambda 1 0 0 and some operator here, because span phi 1 is invariant subspace for T and T is self-adjoint, hence we can conclude that it is reducing. Because of that we get this half diagonal entries to be 0. Now let us define T2 as T restricted to H1 . I am repeating again. Now let us define T2 as T restricted to H2 or T1 restricted to H2. Now this is a map from H2 into H2 as T of H2 is contained in H2. We know that span phi 1 is invariant under T. Since T is self-adjoint, its orthogonal complement, namely H2, is also invariant under T. Hence T2 is a map from H2 into H2. Okay. If T2 is 0, then we can say that T restricted to H1 is 0, then H1 is part of null space of T, or we can say that null space of T perp, that is range of T closure, is part of span phi 1. That means T is rank 1 operator. Now if T2 is non-zero, then we continue the procedure. So then we can say that T2 is self-adjoint and it's also compact, but it's a map from H2 to H2. Now we can apply the earlier lemma again. So by the lemma, there exists lambda 2 in R and phi 2 in the unit sphere of H2. Yeah, it is unit sphere of H1, such that T2 phi 2 is lambda 2 phi 2, and we know that mod lambda 2 is nothing but norm of T2. This is the norm T1, because T2 is a restriction of T1, so this is mod lambda 1. And by the construction it is clear that you can say that phi 1 and phi 2 are orthogonal to each other. Okay, and we know that mod lambda 2 less than mod lambda 1. So we got two eigenvalues, lambda 1, lambda 2, and corresponding eigenvectors phi 1 and phi 2. And it may be possible that mod lambda 2 equal to mod lambda 1. Okay, now next let us take, so define H3 as span phi 1 phi 2, because we want to avoid these two vectors from the space and take the orthogonal complement. Now we know that span phi 1 phi 2 is invariant under T and T is self-adjoint. We can say that it is reducing, hence it is reducing its orthogonal complement, that is H3 also reducing. So we can say that T of H3 is contained in H3. Here T is nothing but T1. So T can be written as here 0, because reducing, this is some operator, and T restricted to span phi 1 phi 2 is exactly lambda 1 0 0 lambda 2. Now let us write T3 as T restricted to H3, which is a map from H3 into H3. Now T3 may be 0, may not be 0. If T3 is 0, then by the earlier observation we can conclude that T is a rank 2 operator. And H3 is part of null space of T. If T is non-zero, we can continue this procedure. Now continuing this procedure, so by continuing this procedure, we get that lambda 1, lambda 2, so on lambda n eigenvalues of T with corresponding eigenvectors phi 1, phi 2, phi 3, so on phi n. And by the construction we can say that each phi j is mutually orthogonal with phi I. So clearly phi j is orthogonal to phi I for all I not equal to j. By the construction, so we have that mod lambda 1 is bigger than mod lambda 2, that is bigger than mod lambda 3, so on. In general, in fact, we can say that mod lambda n is nothing but norm of T1 restricted to Hn. This is how we constructed lambda 1, lambda 2, lambda 3, so on, and the corresponding eigenvectors phi 1, phi 2, phi 3, so on. Now let us look at next step. If lambda n is infinite, we show that it is lambda n converges to 0. This is step 2. If lambda n is infinite, then lambda n converges to 0. Suppose lambda n does not converge to 0, then there exists an epsilon and infinitely many lambda n's such that mod lambda n is bigger than epsilon. Let us take a set S, set of all n in n, such that mod lambda n is bigger than epsilon. Then we can conclude that S is infinite. Okay. Now corresponding to lambda n, we can pick up the corresponding eigenvector. So we have T phi n is lambda n phi n. So consider norm of T phi n minus T phi m square. This is nothing but norm of lambda n phi n minus lambda n phi m square. This is lambda n belongs to, actually n and m belongs to the set S. Okay, so this is nothing but mod lambda n square plus mod lambda m square by looking at the orthogonal, by using the orthogonality of phi n and phi m when n not equal to m. So this is bigger than 2 epsilon square. So this implies that T phi m or T phi n is not Cauchy in H, but phi n is a bounded set, and since T is compact, T phi n should have a convergent subsequence, but we have shown that T phi n is not Cauchy. So this is a contradiction. To the compactness of T. So we got contradiction because we assume that lambda n does not converge to 0. So therefore we can say that lambda n converges to 0 as n tends to infinity. This completes the proof of step 2. Now step 3 is the representation part of T. Representation of T. Let us take x from H. So define xn as x minus summation j equal to 1 to n inner product x with phi j multiplied by phi j. Okay, we can show that this is an element of H n plus 1, because if you look at inner product xn with phi j, so that is nothing but inner product x with phi j minus inner product x with phi j for all j equal to 1 to n. So this is orthogonal to all the vectors span of phi 1, phi 2, phi n. So this is in, we can conclude that this element is in Hn plus 1, span of phi 1, phi 2, so on phi n. Now let us look at case 1. So Tn is 0 for some n, because in the procedure we got that it may be possible that Tn may be 0 after some stage. Now Tn is nothing but T restricted to Hn. So here let us look at element from Hn. So here we have to take n minus 1. So let us make this as element of Hn. Okay. Now since Tn is 0, we have 0 is nothing but Tn xn, but Tn xn is nothing but T xn, because Tn is a restriction of T. So this that means T of xn is 0, that means T of x is nothing but summation j equal to 1 to n minus 1 inner product x with phi j multiplied by T phi j, but T phi j is lambda j phi j. So you will get lambda j inner product x with phi j multiplied by phi j for every x in H. That means T is a finite rank operator. In fact, rank is nothing but n minus 1. Now let us look at case 2. Tn is non-zero for all n in n. In that case, let us look at Txn. So let us we have the same Txn, we can look at norm of Tx minus summation j equal to 1 to n minus 1 lambda j inner product x with phi j multiplied by phi j. If you look at norm of this is nothing but Txn. This is Txn, and this is nothing but norm of Tn xn, because xn is an element of Hn. Now this is less than norm Tn multiplied by norm xn, and this is mod lambda n into norm xn. Now if you look at xn, So x can be written as here, x can be written as xn plus summation j equal to 1 to n minus 1 inner product x phi j multiplied by phi j. So because xn is orthogonal to each phi j for j equal to 1 to n minus 1, so we have norm x square is norm xn square plus norm of the second term square. So hence we can say that norm xn square is less than or equal to norm x square. In term we can say that norm xn is less than norm x. So this is less than mod lambda n into norm x. But we know that whenever lambda n is infinite, then it goes to 0 by step 2. So this goes to 0 as n tends to infinity. This means Tx can be written as summation j equal to 1 to infinity lambda j inner product x phi j multiplied by phi j. Now in fact if you define, so let us look at this as inequality, this whole inequality as double star. So let me define Tnx as summation j equal to n minus 1 lambda j inner product x phi j for every x in H. These are all finite rank operators. Now by double star we get norm of Tx minus Tnx is less than or equal to mod lambda n norm x for every x in H. So this implies if you take supreme over norm x equal to 1, because on the right hand side lambda n is a bounded sequence, we get norm t minus Tn is less than mod lambda n for every n in n. So this implies that Tn converges to T in the operator norm. That means the series of operators on the right hand side converges to T in the operator norm. So they are all finite rank operators. They converge to T in the operator norm. We know that whenever Tn converges to T in the operator norm, if each Tn is compact, T must be compact. So anyway we have assumed that T to be compact, so we are approximating it by sequence of finite rank operators. So this completes the proof of this result in all the cases. So T can be represented using an orthonormal basis of eigenvectors, orthonormal set of eigenvectors. Now if you look at this representation T as lambda 1 0 0 lambda 2 0 0 star. So the way we have continued, we can get a diagonal operator with a diagonal entries as lambda 1 lambda 2 lambda 3 so on. So let us look at some important remarks which we can easily get from the result that we have proved. The first one says that when you look at the representation of T, that is nothing but Tx is summation n equal to 1 to infinity lambda n inner product x with phi n multiplied by phi n. So we can say that left hand side element is a element of range of T and right hand side is span of phi n closure. So we can say that range of T, we can say that range of T closure is nothing but span closure of phi 1, phi 2, phi 3 so on. And we know that range of T closure is nothing but null space of T per, because T is self-adjoint. So from these observations we can say that null space of T per and range of T, because range of T is a subspace of null space of T per, are separable. Because they have countable orthonormal basis. Okay. Now when you restrict T to null space of T per, null space of T per is a reducing subspace. So this operator is a map from null space of T per into null space of T perp. This is again compact and self-adjoint. So let me call this operator as T naught. Now the matrix of T naught with respect to the orthogonal basis 5 1, 5 2, 5 3, so on, that we got. So T naught can be represented using the matrix with diagonal entries lambda 1, lambda 2, lambda 3, so on. Okay. Now when we look at T can be represented using null space of T and null space of T perp. In this way, this is null space of T, null space of T perp, null space of T, here null space of T perp. Now when T is 1 1, when null space of T is 0, so null space of T is 0 implies T is nothing but T naught. If T is null space of T non-zero, so in the earlier case we know that it is represented by a diagonal matrix with diagonal entries lambda 1, lambda 2, lambda 3, so on. In the latter case, when null space of T is non-zero, we can say that T is nothing but 0 0 0, and here it is lambda 1, lambda 2, so we get a diagonal matrix here. So this is null space of T, null space of T perp, null space of T, null space of T perp. On the whole, we can conclude that T is diagonalizable. In fact, T is a diagonal matrix with infinite diagonal matrix with diagonal entries as 0 0 0, then lambda 1, lambda 2, lambda 3, so on. So this number of zeros depends on the dimension of null space of T. So if dimension of null space of T is infinite, we will get the first block to be a zero operator with whose domain and codomain to be infinite dimensional. That means we get infinitely many zeros, otherwise you will get finitely many zeros. So the conclusion is that T is represented by a diagonal matrix whose diagonal entries are given in this way. Okay, so these are two important observations. In fact, we can get many important consequences from the spectral theorem. So we will be discussing those consequences at a later stage. Thank you very much.